Our next speaker is Vincent Noel, professor at the University of Paris and also, I think, director of the PrintUp Institute. Yes,
I
the
hope.
stage is yours.
So let's go. Thank you very much for this introduction. So yes, I am full professor at the University Paris City, and I am the director of the PrintUp Institute, which is a research institute dedicated to printed electronics for health. And today I would like to speak about biosensors because it is our expertise in the PrintUp Institute. So I think that most of you already know that due to personalized medicine attempt, due to pandemics, due to saturation of emergency services and also a lack of analysis labs, there's an urgent need in point-of-care devices, in devices that allow diagnostic when you want and where you are. So the market growth expectation for such application are huge. But before that, before reach the market, there's two main problematics that has to be addressed because many people develop some sensors, and even in the institute, we print some pH sensor, some pressure sensor, and so on. But for biosensor, this is another story, because the first question is how to detect finally a given analyte in a very complex system. And the second central question, which is very important also, is how to manufacture point-of-care devices which will be produced at large scale. So I think that today the most famous point-of-care device is the lateral flow assay. It's allowed to diagnostic some virus. So everybody already use this kind of COVID test. This is clearly a mature technology, but there are some drawbacks. Insufficient sensitivity, no continuous measurements is allowed with such devices, no simple multi-analyte detection, and no digitalization of results. So in the field of biosensor, many people think that it's better to use electrochemical or electrical biosensor more than optical ones and more than such as lateral flow assay. Because electrochemical and electrical biosensor require a low energy to operate, it's very easy to implement such devices with other electronics. You obtain directly an analogic signal. This is not an optical signal. You don't need to have, a detector and so on. And it's easy to monitor it. So in our research team, we focus more specifically on organic electrochemical transistors and electrolyte gate organic field effect transistors. And today, I would like to show you a case study because we developed such devices in the lab, and we had some difficulties now to go to printing techniques and large-scale fabrication process. So just as an introduction, I'm sorry, I'm a professor, so I need to give you some explanation before. What is an electrolyte-gated organic field effect transistor? This is a common field effect transistor with three electrodes, a gate, source, and drain, which are separated by an organic semiconductors. And if you don't apply any voltage to the gate, the charge carrier inside the semiconductor is diluted, is homogeneously distributed inside the materials. And if you apply a sufficiently high gate voltage, so maybe I can do that. For example, you negatively charge the gate, you will accumulate the charge and form a channel. And so if you polarize source and drain electrode, you have a huge drain current. We said that the transistor is in the on states. So an electrolyte gate organic field effect transistor operates in the same way. It's very common operating mode. So here is the output characteristic of such devices. And in such devices, this is very interesting because you can observe that we can switch on the transistors. I'm sorry for this. We can switch the transistor at few hundreds of millivolts. The transistors switch on at less than 1 volts. So it could operate at very low voltage. So what is really interesting for biosensor is the specificity of electrolyte-gated organic field effect transistor, because in this kind of transistors, the conventional dielectrics is replaced by a